In this video, I'll be going over how to balance chemical equations. So chemical equations need to be balanced with respect to two different properties, mass and charge. So that means for every chemical equation, you need to have the same number of elements on both sides of the arrow, that's mass balance, and you need to have the same overall charge on both sides of the arrow, that's charge balance. We'll start with the inspection method of balancing chemical equations. Now, the inspection method works best for the more simple and straightforward chemical equations. It doesn't work as well for the more complicated chemical equations that you'll see. We have other methods of dealing with the more complicated equations, but for the simple ones, like the one you see here, the inspection method works really well. So to use the inspection method, what you'll want to do is take a tally of the number of elements that you have on one side of the equation, then take a tally of the elements you have on the other side of the equation, and then you can see what you can do to balance both of them together. So we'll start with the left-hand side of the equation. So here in our first compound, we have 1 sodium and we have 1 chloride. Here in our second compound, we have 1 barium and we have 2 fluorides. Keep in mind that this subscript 2 next to the F indicates that we have 2 of those in the compound. Now moving over to the right side of the equation, in our first compound we have 1 sodium and 1 fluoride. Moving to our second compound, we have 1 barium and we have 2 chlorides. So right off the bat we can see what we have balanced already and what isn't balanced. So the number of sodiums and the number of bariums are already balanced, but the number of chlorides and the number of fluorides isn't balanced on both sides. So what you can do is take a look here at your compound here, this barium fluoride, and say, well, here I have 2 fluoride ions, and over here in this sodium fluoride I only have 1. So to balance the number of fluorides, what you can do is stick a 2 as the coefficient in front of this sodium fluoride. And what that does is it now gives you not 1, but 2 fluoride ions. And that balances the number of fluorides. However, it also changes the number of sodiums that you have. So instead of 1 sodium, we now have 2. So while we've balanced the number of fluorides, we've unbalanced the number of sodiums. And the number of chlorides is still not balanced. So you can look at your compounds and you can say, well, I have this sodium chloride here. I need 2 chlorides on that side, and now I need 2 sodiums on that side. So if I stick a 2 in front of the sodium chloride, that now gives me 2 chlorides, and it gives me 2 sodiums. So that now balances the number of chlorides that we needed to begin with, and it balances the number of sodiums that we created when we added a 2 to this compound. And after we do all that, you can see that we now have a balanced chemical equation where we have the same number of every element on both sides of the arrow. And that's generally how you're going to use the inspection method. You're going to go through, you're going to take a tally, and then you're going to start manipulating the equation until you get it just right. And you can see how this works relatively well for these simple equations. However, it will get incredibly frustrating if you do this for more complicated equations where you have more and more numbers of each element to have to worry about when you're doing this balancing. So that's well and good for this one. Let's look at another example of the inspection method using polyatomic ions instead of just strictly elements. So looking at this equation here, we have now what are called polyatomic ions to look at. So an example would be this here. This SO4 is one singular group, and it's called a sulfate ion. So the sulfur and the 4 oxygens are bonded together in a group, and they together make one singular ion, called a polyatomic ion. The same thing is true for the nitrate here, this NO3, where the nitrogen and the 3 oxygens are bonded together in one group, and they have a charge. And the trick to using these when balancing chemical equations is to treat them as one single group rather than separate elements. If you do that, it'll make balancing these a lot easier when you have these polyatomics. So we're just going to go through and use the same method we did before by taking a tally of everything we have on both sides. Okay, so I went ahead and took a tally of everything, and you can see that we only have 2 things out of balance in this equation: sodium and nitrate. We have 2 sodiums and 2 nitrates on this side, on the left side, and on the right side we only have 1 sodium and 1 nitrate. So therefore, since they're in the same compound, it makes it a little easier. If we stick a 2 here, that will now give us 2 sodiums and 2 nitrates. And that balances the entire equation by just doing one simple thing. And that's why this trick works really well, because when you think of the polyatomics as just one singular group rather than separate elements, it makes it a lot easier to just count that group as one thing. Makes it a lot easier to balance. So now let's look at a different method that you can use for the more complicated chemical equations that you'll see. And it's called the algebraic method of balancing. So here we have a more complicated chemical equation than what we've seen before. And so to deal with these, you can always use what's called the algebraic method of balancing. The algebraic method seems a little complicated at first, but I promise if you practice it enough and you use it enough, it should become relatively straightforward. Now, hypothetically, you could use the inspection method to balance this equation. It would just take a lot of time, and it would probably be pretty frustrating to do it that way. It would be a lot of trial and error. Whereas using the algebraic method, it will never steer you wrong if you do it correctly. Now, on quizzes and tests, time is everything, so the faster you get at the algebraic method, it's usually a lot better because it's pretty fail-proof in terms of always getting you a balanced equation. So the key to the algebraic method is to assign each compound in your reaction with a letter as its coefficient. So since we have 4 compounds here, I'm going to make this one A, this one B, this one C, and this one D. Now what we're going to do is for each element in each compound, we're going to take the number of that element and pair it with the letter in front. So I'm going to take each element, in this case we have carbon, hydrogen, and oxygen, and I'm going to pair the number with the letter. So for carbon, we have 4 carbons and it's paired with the letter A. So I'm going to write this as 4A. For hydrogen, we have 10 hydrogens and it's paired with the letter A. So I'm going to make hydrogen 10A. For oxygen, we have 2 oxygens and it's paired with the letter B. So I'm going to write oxygen as 2B. And over here, we're going to do the same thing on the right side of the equation. So I'm going to take our elements again, carbon, hydrogen, and oxygen. For carbon, I have 1 carbon and it's paired with the letter C. So I'm going to make this 1C. For hydrogen, we have 2 hydrogens and it's paired with the letter D. So I'm going to make this 2D. D. And for oxygen, we have a slightly different scenario here, where we have two oxygens paired with the letter C. So I'll write that as 2C, but we also have one oxygen paired with the letter D. So I'm going to add that additional variable here for oxygen as adding 1D to the 2C. So one of the key things you want to do here is set both sides equal to each other for each element. So what we're doing is we're setting the carbon on the left side equal to the carbon on the right side. So what we're doing is we're setting 4A equal to 1C. And really the key factor here is you're going to let A equal 1. Because that would make it a lot harder if we didn't have anything to work with. But letting A equal 1 gives us something to work with. So if we start with the carbon and we say 4A, and we're going to substitute 1 for A, equals 1C. Well, 4 times 1 is 4. Divided by 1 is just 4. So this means that C must equal 4. And I'm going to keep a running tally of all of my variables up here. So we know A equals 1, and now we've solved for C, and that equals 4. So now let's go ahead and do hydrogen. So for hydrogen we have 10A, and I'm going to substitute A for 1, equals 2D. So 10 times 1 is just 10, and if we divide the 2 over, that means that 10 divided by 2 is 5, so D is equal to 5. And I'll put that up here as well. So now we just have one variable left to solve for. And I'm going to erase some of this to make room. So now we have oxygen. So for oxygen, we're going to say 2B is equal to 2, and we're going to substitute 4 for C, plus, and we're going to substitute 5 for D. So 2 times 4 is 8, plus 5 is 13. So that simplifies down to say that 2B is equal to 13. Divide the 2 over, and we get that B is equal to 13 halves. So now that we have all the variables solved for, we can go ahead and plug them in as our coefficients in the reaction. So what I've done is gone ahead and plugged in everything for the variables that we solved for. And this is technically balanced, however, we generally don't want fractions in our final balanced equations. So this 13 halves kind of sticks out like a sore thumb. We typically want non-fractions as our coefficients. So what we can do is, since 2 is the denominator here, we can multiply everything in the equation by 2. By multiplying everything by 2, this will cancel the fraction here, and that will give us all whole numbers for the balanced equation. So once you multiply everything by 2, the fraction cancels, and now we have our final balanced equation with no fractions. And just as a way to check yourself to make sure that your equation is balanced properly, you can always go back and take a tally of how many elements you have on both sides, and they should be equal once you're finished with the algebraic method. If they're not equal, that means you might have made a mistake somewhere, and you can go back and look and correct that if you have time.